Hello, hello, hello. Hopefully this one will be the end. And the last one, if the computer doesn't go crazy on us, which should work for the whole shebang. So let's take a look at it. Um, we want to find the bond enthalpy of O double O. So we're going to pretend in the box we have up above that O double O is not there. So what I'm going to do is, notice how we've got balanced equations here. I'm going to write out what each of these are going to do. Whoops, I put 2 there. I have 1, 2, 3, 4, 5, 6 times 2. So I have 12 C to H's. And I have, again, coefficient of 2. So I have 2 C to C's. That takes care of those. Then I have plus 7. I'm going to call that X because that's what I'm going to solve for. Because that's O double O. Boop, boop, boop. Plus, this is my negative side. So I got 1, 2 times 4, 8 negative C double O's. Plus 1, 2 times 6, 12 negative OH's. O to H. And then that's going to equal negative 2,800. So let's see what we can get out of these up here. Oh, where's my bond energies? C to H is 413. So, oops, I didn't go far enough down. 12 times 413 plus C to C, 2 C to C's, 2 times 348. Plus 7x plus 8 times C double O. C double O right here, 799. So negative 799. 8 times negative 799 plus 12 times negative whatever OH is going to be. O to H, negative 463 equals negative 2,800. So let's calculate this bad boy out. We'll get 7x plus something. So 12 times 413 plus quantity 2 times 348, close quantity, plus quantity 8 times negative 799, close quantity, plus quantity 12 times negative 463, close quantity. And that is negative 6296, negative 6296 equals negative 2,800. So 7x equals, got to add negative 2,800 plus negative, not plus negative, just plus. So it's just plus, got to delete that. 6296 equals 3496. So x is, divide that by 7, 499 kilojoules per mole. And that's it. All right. 2 nitrogen atoms combine to form a single nitrogen molecule or some other following equation. Use the table of bond energies below to determine the bond enthalpy change for the reaction. So notice I have N plus N yields, I hope you know, nitrogen's triple bond. If not, draw the loose dot structures. Connect the dots. La, la, la. To find the enthalpy change, it's going to be negative 950 kilojoules mole to the negative 1. Use the equation below to answer the questions that follow. From the amount of energy released when 4.5 moles is used in the reaction, 4.5 moles of O2, 4.5 moles of O2 times dividing bar, HU moles of O2. And I need an equivalency between O2 and negative 1120. So remember how we talk about this would mean plus 1120 kilojoules. And kilojoules are just like moles. Coefficients right there. So 4.5 times negative 1120 divided by 3. Now notice it says how much energy is released, so I really don't need the negative sign here. So it's 1680 kilojoules. All right, determine the energy released when 18 grams of water are formed. Energy released when 18 grams of water are formed. So 18 grams of H2O times 18 grams of H2O in 1 mole. Notice I'm going through moles times moles of H2O and 1120 kilojoules. I forgot the coefficients of water is 2 So 18 divided by 18 is 1, so it's just 1120 divided by 2, which is 560. And that's released. So that would be negative, but really that sign doesn't matter much because the directions tell you what it is. All right. So amount of energy released when 1.45 grams of SO2 are formed. 1.45 grams of SO2. Hey, 2 grams of SO2. Going to moles of SO2. 1 mole is 32.07 plus 32, which is 64.07. Then I got moles of SO2, and then I have kilojoules. So still 1120, and my moles of SO2 would be 2 equals 1.45 divided by 64.07 times 1120 divided by 2 equals 12.7 kilojoules. Determine the mass of H2S used when 150 kilojoules are released. 120, so 150 is 120 kilojoules. H2 kilojoules, just like everything else. I'm putting kilojoules on the bottom to cancel kilojoules. Moles of H2S on top, 1120. And now I've got to find the coefficient for H2S. I was hoping it would remember it. Coefficient for H2S is dose. So that's 1120. So this is 2. Determine the mass used times dividing bar, 1 mole H2S. Go to the periodic table of H2S. 32.07 plus 2.02 is 34.09. So 120 times 2 divided by 1120 times 34.09 is 7.35 grams of H2S used. Not too bad. Cooking along, cooking along. For reaction in C, okay, amount of energy released. Reaction in C, the energy released is usually 250 grams of water. If the water is initially at a temperature of 25, determine the final temperature of the water. So no energy is lost. So I'm looking at Q equals MC delta T. Q is a number I'm going to get from C in a minute, but I have 250 grams of water. Specific heat of water they're telling us to use is 4.2. I did check to make sure that it's grams. Grams. And the change in temperature, we got to find T sub F minus 25. And then C was the amount of kilojoules we used. So where's C? Oops, I shot right by it. 12.7 kilojoules, which is going to be 12,700 joules. Okay, so there's that stinking unit thing that gets in our way again, right? So let's solve for T sub F minus 25. 12,700 divided by 250 divided by 4.2. So I have 12.09 joules equals T sub F minus 25. So do you see how I divided by this and divided by that? So then what I'm going to do is I'm going to add 25 to both sides. So 12.09 plus 25 is 37.1. T sub F equals 37.1 degrees Celsius. Determine the mass of H2S required to react in order to bring 100 milliliters of water to a boil. The initial temperature of the water is 20, and density of water is 100 grams per milliliter. So that means 100 milliliters is 100 grams, right? Density, 1 gram, 1 milliliter. 100 milliliters would be 100 grams. Initial temperature is 20, and the specific heat capacity of water is 4.18. Isn't it funny we just changed it? So water, 100 to a boil, so I got to make it all boiling. So that means Q equals MC delta T plus M. To a boil, so it's not going to boil. It's just going to be to a boil. My bad. So we don't have to calculate the energy to boil it. So we're going to look at 100 grams. Specific heat of water is 4.18. Change in temperature, 20 to 100 is 80. So 100 times 4.18 times 80 is 3340 joules. Okay. So I'm going to change that to 3.34 kilojoules because that's the what we're going to use with our balanced equation. So remember how we had 1120 kilojoules per mole? So 3.34 kilojoules times 1120 kilojoules. That's the coefficient for kilojoules. And we're doing moles of H2S. Oops. And I got to get out of moles of H2S and go into grams of H2S. So that was 34.09. I remember that. I forgot the coefficient for H2S. Oh, there it is. It's 2. So this tells the grams I need to react this. 3.34 times 2 divided by 1120 times 34.09. I want to say again, the toughest part of this was to remember to do this part, I think. Of course, I could be wrong. That's going to be 0.2, wow, 0 grams H2S. It's not very much. Oh, it's because I'm dividing by 1120. That would make sense. Determine the moles of SO2 formed from the reaction above if the energy from the reaction is used to melt 120 grams of ice. Okay, moles of SO2 formed if the energy from the reaction is used to melt 120 grams of ice initially at 0. So I got to do this Q part first. I'm melting only, delta H fusion. The ice is at 0, so I don't have to change the temperature of it. 120 grams of ice. Delta H fusion is, I'm going to go ahead and make it kilojoules right now. So I'm going to make that kilojoules 0.334 kilojoules. That way it'll work a little better on the next part. I want to fix that as soon as I can so that 40.08 kilojoules, so I don't forget. Moles of SO2 formed. So now I'm going to start with 40.08. And try that again. 40.08 kilojoules times 1120 kilojoules and moles of SO2. So I got to find the coefficient for SO2. There it is, 2 moles of SO2. That's not oh yeah, it is kilojoules. So here we go. 40.08 times 2 divided by 1120. Again, it's going to be small because I'm dividing by 1120. That's going to be 0.072 moles of SO2. And SO2, of course, smells like rotten eggs. Or as your family says, rotten eggs. Use the equation below to answer the question of following. Determine the amount of energy released when 20 milliliters of 0.75. Okay, energy release. So I see this whenever I see molarity. I know I'm going to use moles equals molarity times volume. 20 milliliters. I spit on you. 0.020 liters. So my moles are going to be 0.75 times 0.02. So my moles are going to be 0.75 times 0.02, which is going to be 0.015. Better label that HCl. Determine the amount of energy released when that much is used. So I'm going to start with 0.015 moles of HCl. I'm going to hit you moles of HCl, put you on the bottom to cancel. I'm going to go into kilojoules. I still like to put it on the correct side. Notice it's going to be a positive. The sign changes. That sign tells me it's on the right. 57.1. HCl's coefficient is 1. So 0.015 times 57.1. I did quick check that it was balanced. So whenever there's no coefficients, you always got to make sure it's balanced because that'll get you. When 100 milliliters of 1 molar and 100 milliliters of NaOH reacted, 5.71 kilojoules of energy is released. When 100 milliliters of 2 molar HCl is reacted with 100 milliliters of NaOH of 1 molar, it's still, explain why. In case 1, both are limiting reactants, equal moles. Case 2, the limiting reactant is use here, of 2 molar HCl, so it's not HCl, is NaOH. Same limiting reactant, same product, which would still be 5.71 kilojoules. When 25 milliliters of unknown molarity HCl's react with excess NaOH, 2.55 kilojoules of energy is released. So let's go 2.55 kilojoules times, I hate you kilojoules. I'm going to go into moles of, I want HCl. So I remember that was a 1, but I forgot my kilojoules. 57.1. 57.1 kilojoules. So that will tell me how many moles I need. 2.55 divided by 57.1 is 0.0447. So if I've got to find molarity, we all know moles equals MV. So 0.0447 equals molarity, which is what I'm solving for. And the volume is 25.025 liters. So my molarity equals 0.0447 divided by 0.025, 1.79 molar. Good. No, stay there. So take my deep breaths. My pen will stay there. Maybe I can even erase this line. All right. According to the information provided in the table above, a 1 gram sample of which compound would contain the greatest mass of chlorine. Oh, this is the review stuff. So what you're going to do, each of these has 1 Cl. So a 1 gram sample would be which one would have the greatest mass. So that means that the one with the biggest Cl, percent Cl, which would mean the one with the smallest molar mass of other. Okay, so sodium I know is 22.99, lithium is 6.93, copper is 63-ish, cesium is big. I don't even know what it is, but this is going to be my answer. So it's going to be lithium, LiCl. With the calculation, there you go. You just saw that. So percent equals chlorine over metal chloride times 100%. So that means the smallest number, biggest percent, would have that. All right. A student adds excess HCl to 150 milliliter solution containing Ag positive and precipitates Ag positive silver chloride ion, silver chloride AgCl. Student collects the precipitate in a pre-weighed piece of filter paper. Precipitate and filter paper are rinsed with distilled water, dried, and weighed. The data from the experiment are given in the table below. Determine the moles of AgCl that precipitated. So first thing I'm going to do is grams of AgCl that precipitated. So 2.311 grams minus 0.851 grams is going to give me grams of silver. 2.311 minus 0.851 is going to give me 1.460. And I want to change that into moles. Grams of Ag, 1 mole of Ag. I'm counting on my memory here. I don't have a periodic table. Let's see if Siri can help me. I think it's 107.9. No, 107.87 memory. Problem solved. 107.87 is the molar mass of silver. So 1.46 divided by 107.87 is 0.0135 moles of Ag. Calculate the original molarity of Ag positive in the solution. Assume all of the Ag positive precipitates. So I'm doing molarity. Notice I've got a volume here. So moles equals MV. My moles were 0.0135. My volume is 0.15. It was 150 milliliters. Solve me some M. So divided by 0.15, I have molarity equals 0.0902 molar. All right. Oops. Gotta slow down a whisker, I guess. Okay. No, that's bonus stuff. What's the definition of standard enthalpy of formation? Energy to make a compound from its elements. And I have to adjust that. To make 1 mole of a compound from its elements. Write the reaction with standard enthalpy of formation of the following compounds from their constituent elements. Here we go. These are fun. Mg plus, plus C plus O2 yields MgCO3. I need to make this 3 halves. 3 halves. That way it's balanced. And notice how I have a coefficient of 1. Be nice to erase the slop. There you go. That's 1. C6H12O6. Carbon plus H2 plus O2 yields C6H12O6. I need 6 carbons. I need 12 hydrogens. I need 6 oxygens. Carbon plus O2 yields CO2. N2 plus H2 yields NH3. Throw a 2 in there. Oh no, I can't put a 2 in there. I have to have a 1 for my coefficient. 1 half. And then this would be 3 halves. Okay. All right. Nice and patient. So it'll stick. Good. Yay. Here we go. Enthalpies of formation to calculate delta H for reaction. So notice these are compounds. So this is going to be delta H products minus delta H reactants yields delta H of the reaction, which is what we're doing. Use the standard enthalpies of formation above to calculate delta H of the reaction. So product C2H6, is it balanced, first of all? It is. C2H6 is negative 0.68. Products minus reactants. C2H4, 52.30, plus hydrogen. Oh, it's an element at standard state. That's 0. Equals, let's do it. Negative 84.68 minus 52.30. It's odd that that has a positive number. Negative 136.98 kilojoules. Next one. 3NO2. Oh, we got to do, again, it's products minus reactants. So 2 times HNO3 is negative 134.3 plus NO 90.37 products minus, distribute the negative, NO2 33.84. 3 times 33.84 plus liquid water, only one, negative 285.83. Now I have to distribute this negative sign. So I'm going to make this a plus, make that a minus, make that a plus. I know that distributing negative signs are a mistake that I make from time to time. So I try to get rid of that problem as soon as I can. So 2 times negative 134.3, enter, plus 90.37, plus quantity 3 times negative 33.84, close quantity, plus 285.83 equals 6.08. That's itty bitty. Oops. And that's it. All right. So again, products minus reactants. Let's see if I can make this a little smaller so it fits in there. Products minus reactants. So I have 4 times water, which is negative, it's gaseous water, negative 136.10. Other reactants plus 0, minus, distribute it, N2O4 is 9.66, plus 4 times hydrogen gas, which is 0. So here we go. 4 times negative 136.10 10 minus 9.66 equals negative 554.06 kilojoules. All right. It never ends, never ends. Determine the standard enthalpy of formation of nitromethane using the equation below and the standard enthalpies of formation from the table above. So this means we're going to do the same thing, right? So products minus reactants. So I'm going to start with 2 times negative 393. I know a few of these. That's CO2. Plus 3 times negative 286. That's water. Plus 0. Minus, distribute it. 2 times, I'm going to call it x. I like to have my x's. Plus 3/2 times 0. Equals negative 1418. So here we go. 2 times negative 393, enter. Plus quantity 3 times negative 286, quantity, enter. So negative 2x equals negative 1418 plus, this was negative, this whole thing together was negative 1644. So it's going to be plus 1644. So negative 1418 plus 1644 equals, divided by negative 2 equals negative 113 equals x, and that is C2 kilojoules. And that is CH3NO2. All right. In an experiment, liquid heptane is completely combusted to produce this and that, as represented by this. The heat of combustion for 1 mole of it is this big bad dog right there. Determine the enthalpy of formation of this. So this is the heat of combustion, enthalpy of formation of this. So what that means is all I have to do is solve for this guy. Okay. Same thing, products minus reactants. I'm going to do it in this space right here. Products are going to be 7 times negative 393. Again, I sadly remember CO2. Plus 8 times negative 286, because we use water a lot. Minus x plus 11 times 0. Actually, 0, it's an element at standard state. Equals negative 4.85 e negative 3. So let's collect the left term. So 7 times negative 393.5 equals, plus quantity 8 times negative 286, close quantity, is negative 5042.5 minus x equals negative 4.83. I'm sorry, 4.85 e negative 3. So then I'm going to kick this to the other side and divide by a negative x. So 4.85 second comma negative 3 plus 5042.5 equals, and then make it negative. So x equals negative 5043 kilojoules, which equals C7H16. There's a negative sign there. All right. A certain reaction has a delta H of negative 25 kilojoules per mole. What would the delta H be for the opposite? You just change the sign, plus 25 kilojoules per mole. The reaction below is the sublimation of iodine. Would you expect the sublimation of iodine to be endothermic or exothermic? You're going from solid up to gas. Going up, absorb it. Endo. Bonds break. No, so I was going to be okay with that until I saw it say indicate bonds. The energy required of saline. 1 mole of iodine is the same. It would be for 1 mole of solid iodine to liquid, and then liquid to gas. Explain why, referring to what is occurring with intermolecular forces. So the same break of close solids to loose, let's put loose liquid to far gas. The same thing if I just go from close solid to far gas. So they're the same bond breaking happens. Okay. So they're breaking in each one. All righty. All right, use the reaction given below to find delta H in kilojoules per mole. So on this one, I'm going to do some flippy here. Delta H of the reaction. So I'm trying to make I2 solid turn into I2 gas. So I want I2 solid. Well, I like to put I2 gas on the right-hand side. So we're going to flip this. It's going to have high yields. Well, I need a whole one, right? Yeah, so I'm going to flip and multiply by 2. So 2 high plus yields H2 plus I2. And I'm going to focus on the gases here. So that's what I want. And then on this one, I have to multiply this one by 2, but leave it where it is. So H2 plus I2 solid yields 2 high. And when I look at those will cancel out. And I have I2 solid yields I2 gas. So I math this out. So 26 times 2 is 52. And then this one's going to be positive 5 times 2, so positive 10. That's 62. All right. Cruising. Well, I sure hope this is the last page, is it? Nope. So I'm going to hit pause.